Today in section 6.3, we're going to talk about a new kind of function. The new kind of function is called exponential. Anybody know what makes a function exponential? That has a rate that increases over time. That's correct, actually. But how does it look like in an equation? It has exponents. Okay, so here's an equation that has an exponent. But that equation is not called exponential. In fact, we already know what kind of equation that's called. What kind of equation is that? What do we call an equation that has an x squared? That's called a quadratic. This one's quadratic. So what do we mean by exponential? It's not just that they have exponents. There has to be something special about the exponent. They look like this. That one would be called an exponential function. So what's special about the exponent? It's the variable. The variable is in the exponent. So that's what we mean when we say exponential function. Not just that it has a variable, but the variable, not that just that it has an exponent, I mean. It means more. It means that the exponent is a variable. It has an x in it. That's what we mean by exponential. All right, so primarily what we're going to do in this section is we're going to graph these things. And at this point in our life, we really don't know much about an exponential function. So in order to graph, probably the best way to start is to build yourself a little table. Pick a couple of your favorite numbers. What are some of your favorite numbers in the whole wide world to plug in? 0, 1, and 2. And how about a couple of your favorite negative numbers in the whole wide world? -1 and -2 would be excellent choices. Okay, what do I get when I plug in 0? How much is 2 to the 0? Not 0.
1.
It's 1. Anything to the 0 power is 1. That was one of our rules of exponents, as long as your base is not 0. And how about 2 to the 1? 2. And 2 squared? 4. Now, here's why we went and did all this work on exponential function, on exponential properties, really, was so we could talk about exponential functions. How much is 2 to the -1? What does a negative exponent do? Puts it on the bottom. So 2 to the -1 is another way of writing 1 over 2. It's another way of writing 1/2. How about 2 to the -2? 1 over what? Not -1. Negative exponents don't give negative answers. What do negative exponents do? They make fractions. So what this negative power is going to do is it's going to drop that to the bottom. So that's going to be 1 divided by 2 squared. But 2 squared is just a fancy way of saying 4. So that's just 1/4. Negative exponents never give negative answers. Negative exponents make fractions. All right, so looking at this, it looks like we have 0, 1, 1, 2, 2, 4. What would happen if I plugged in 3? I'd get 2 cubed. 2 cubed is 8. So what happens here? This starts to grow really fast. 4, 5, 6, 7, 8, 2, 8, 3, 8 would be way up there. If I plugged in 4, I'd get 16. The exponential functions go up really, really fast. And then what happens with the negative numbers? If I plug in -1, I get 1/2. If I plug in -2, I get 1/4. What's going to happen if I plug in -3, -4, -5? it's going to get closer and closer to 0, because if I plugged in -3, I would have 1/8. If I plugged in -4, I'd have 1/16. It's going to get closer and closer to 0, but is it ever going to hit 0? No, and there's a name for that. There's a name for when a graph gets closer and closer to a line, but never hits that line. What's that called? Say that again? Asymptote, that's correct. So, you're going to be asked to graph these functions. So there's the graph. And then you're going to be asked to find three things. You're going to be asked to find the domain, the range, and the asymptote. All right, so domain and range, we haven't used those words in quite some time in this class. What does domain mean again? The x numbers. So the domain means what kind of x numbers can you plug in? We could plug in all of them, couldn't we? We plugged in some positive numbers, we plugged in some negative numbers, we plugged in 0. Is there any restrictions? No, I don't think so. Domain is all real numbers. Range means the y numbers. What kind of y answers do we get? Well, all the y numbers that I have in my table are positive numbers, aren't they? Am I ever going to hit 0? And I'm never going to get negative either, am I? So what's my range? What kind of y numbers can I get? All numbers greater than 0. So we typically write that way. The range is y is greater than 0. And then what's the asymptote? The asymptote is the line that the graph is getting really, really close to. Well, this graph is getting really, really close to the x-axis. How do you write the equation for the x-axis? Not x equals 0. X equals 0 would be the y-axis, because this would have 0, 1, 0, 2, 0, 3, 0, 4. The x-axis is y equals 0, because it would have 1, 0, 2, 0, 3, 0. The y number would always be 0 for the x-axis. Questions on that one? All right, now let's change it a little bit. What if I asked you to graph y equals 2 to the x minus 3? Once again, I personally would begin by building a table. I would plug in 0, my two favorite positive numbers, 1 and 2, maybe even 3. And then I would plug in some negative numbers, -1, -2, and we'll even go all the way down to -3. Bless you. I plug in 0. What's 2 to the 0? 1. What's 1 minus 3? -2. I plug in 1. 2 to the 1. 2. 2 minus 3. -1. Plug in 2. 2 squared is 4. 4 minus 3. +1. And then plug in 3. 2 to the third is 8. 8 minus 3. 5. Now, you might have heard that when I asked what exponential functions were, I think Caleb said they're functions where the rate of change is always changing. And notice that that's what's happening. If I go from here to here, my slope would be 1. But if I went from here to here, my slope would be 2. From here to here, my slope is 4. So the rate, the slope, in other words, is always changing. It's never the same. In fact, it has a pattern. It went 1, 2, 4. The next one would be, if I kept going, if I plugged in 4 and 5 and 6. 1, 2, 4. What's the next number? 8, and then 16, and so on and so forth. Okay, now let's try plugging in some negative numbers. What's 2 to the negative 1? 1/2. So this is going to be 1/2 minus 3. What's 1/2 minus 3? Negative 2.5. Okay, that'll work. And then I plug in negative 2. 2 to the negative 2. 1/4. 1/4 minus 3. Negative 2 3/4. All right, and then I plug in negative 3. 2 to the negative 3 is 1/8 minus 3. 1/8 minus 3. Negative 2 7/8. All right, so drawing our graph. We have 0, negative 2, 1, negative 1, 2, 1. So when I draw those first 3 dots, it almost looks like a line, doesn't it? But it's not quite. You draw the next one, 3, 5, and then you see it's certainly not going to be a line. And then we have negative 1, negative 2.5, negative 2, negative 2 3/4, negative 3, negative 2 7/8. So what's happening this time? The asymptote is negative 3. Negative 2.5, negative 2 3/4, negative 2 7/8. I'm getting closer and closer to negative 3, but I'm actually never going to hit negative 3. I missed a little bit there. You draw a nice smooth curve. Now usually when you have an asymptote and the asymptote is not the axis, the way we draw that is we draw it as a dotted line. So we would draw a dotted line right there to indicate that that's an asymptote. The graph is going to get closer and closer and closer to that line, but it's never going to hit it. Once again, you would be asked to find the domain, the range, and the asymptote. Domain. All real numbers. We were able to use positive numbers, negative numbers, 0. There weren't any restrictions at all. Range. What kind of y numbers am I getting? All of them as well? No, I don't think so. It's never going to go down below negative 3, is it? Y is greater than negative 3. I can never hit negative 3, because I can never hit that asymptote. I can never go below negative 3. So it's just y is greater than negative 3. And the asymptote, we already answered that question. Y equals negative 3. So, by putting a number out here, like a negative 3, what did that negative 3 do to the graph? It just lowered it. It took the whole graph, slid it down 3 spaces. What if I had put a plus 3 there? What would it do? It would move it up. So it changed the asymptote to be y equals positive 3. So a number out here just moves the graph up and down, just changes the asymptote. That's all. These 2 graphs that I've drawn, these are both called exponential growth. Why are those called exponential growth? It goes up as it goes to the right. That's called growth. Going up as you go to the right is called growth. What would we call it if it went down as it went to the right? Exponential decay. Let me give you an example of an exponential decay problem. Y equals, let's use a different number. 1/4 to the x. Once again, as usual, I'm going to build myself a nice little table. I'm going to plug in 0, 1, and 2, and -1 and -2. Hopefully that'll be enough numbers. We'll see. What happens when I plug in 0? How much is 1/4 to the 0? 1. Anything raised to the 0 power is always 1, except for the number 0. And then I plug in 1. What's 1/4 raised to the 1? 1/4. How about 1/4 squared? Well, 1/4 times 1/4, you multiply the tops, multiply the bottoms. 1/16. 1/4 times 1/4. All right, now how about 1/4 raised to the -1? What does a negative exponent do to a fraction? It flips it. So this is the same as 4/1 raised to the first, which is, of course, a fancy way of writing 4. 1/4 to the -2. The negative flips it. So that's going to be 4/1 squared. Negative exponents take things that are on bottom and put them on top, and they take things that are on top and put them on bottom. So in other words, if you have a fraction and a negative exponent, the negative exponent is just going to move the top and move the bottom. That's 16. All right, so our picture would look like this. We have 0, 1. We have -1, 4. We have -2, 16. That's way up off the top of the paper already. We have 1, 1/4. We have 2, 1/16. The graph is going to look like so. It's going to be exponential decay. What's my domain? All real numbers. What's the domain for every exponential function? The domain will always be all real numbers for an exponential function. How about the range? What kind of y numbers am I getting? Only positive, so y is greater than 0. And my asymptote? Y equals 0. We're getting closer and closer to the axis, but never touching it. Questions on graphing exponential functions? What are exponential functions good for? Anybody ever seen an exponential function in their life before?
Financial predictions.
Financial predictions are made using exponential functions. If you put your money in a bank and it earns interest, earning interest is an exponential growth pattern. Now, what's the problem with putting your money in a bank and earning interest? The problem is the interest rate today is so incredibly small. What kind of interest rates are you getting today? What's that? It's worse than single digits. I think the last time I looked, the interest on my savings account was 0.3%. Which means, instead of having the number 2 here as my base, I would have 1.0003. So I am getting exponential growth, but because that base is so small, it takes forever for the curve to go up. So interest rates today are so bad that you do have exponential growth, but it's not very good growth. Where else do you see exponential growth or exponential decay? Anybody know? Population. The population of the human race right now has this basic curve, where I think the number of people on this planet is doubling like every 17 years or something like that. exponential growth pattern. That could be a bad thing. How come?
Resources.
Yeah, eventually we're going to run out of resources. So something bad is going to happen there. How about exponential decay? Anybody know where you have exponential decay? The graph's going down like this one.
I'm going to say inversely resources.
No, I don't think so. I think at this point our resources continue to climb. We're getting much, much better at finding hard oil deposits and actually getting the oil out of the ground and cold deposits and things like that. I think at this point our resources actually continue to go up, but they're not going up exponentially. And so what's going to happen is eventually our population is going to pass our available resources. I don't think those are decaying right now. It will eventually. Anywhere else where you might see exponential decay? There are two very common examples that we will talk about later in this class. One of them is radioactive decay. What do I mean by radioactive decay? Like half-lives. What's a half-life? The time it takes for half an element to decay. So if something has a half-life of 10 years, and you start with a pound of it, how much are you going to have 10 years from now? Half a pound. Half of it will decay. What we mean by decay is that it will stabilize and no longer be radioactive. You'll still have a pound of material, but only half of the material will be radioactive. So that's a very common example of radioactive decay. The other very common example of decay that we'll talk about is temperature. What happens when you take something that's really hot and you take it out of the oven? It starts to cool. And it cools, it gets closer and closer to what? Whatever the temperature of the room is. So you would have an exponential decay. Your asymptote would be up higher. Your asymptote would be up at room temperature, but the thing would be very hot. It cools very quickly at first, and then it slows down and it gets closer and closer to room temperature. So that's an example of exponential decay. That was known as Newton's law of cooling, named after that famous Newton guy. All right, so those are the sort of things we're going to be looking at in the near future, kind of examples we're going to be working on with exponential functions.